Um, think about the oldest piece of human technology that you'll interact with today. I mean, it's probably sitting right in front of you right now.
Yeah, almost definitely.
Like the glass screen on your device, or maybe the window in your room, the cup on your desk. Glass making is just this incredibly ancient, fundamental art.
It really is. Yeah. I mean, at its core, you just take silica, which is
Mhm.
sand, and you apply massive amounts of heat.
Right. You shape the molten material, and then you just let it cool down into a transparent solid.
Exactly. And because we've been doing this for millennia, it feels like this completely solved area of engineering, you know?
It definitely carries the sense of permanence. Like, we rely so heavily on those fundamental principles of heat and chemistry to just, well, build our modern world.
We do.
Yeah.
But when we transition from those traditional silica glasses into the realm of modern material science, the definition of what glass can actually be changes entirely.
Oh, complete.
We're looking at engineered materials now that can actively filter the environment, including glass that is specifically designed to trap greenhouse gases like carbon dioxide straight out of the atmosphere.
And that right there is the focus of our deep dive today. So welcome.
Glad to be here.
We're pulling from this really fascinating May 22, 2026 article published in technoscience.net, which is covering a major materials science breakthrough that was recently detailed in the journal Nature Chemistry.
Yeah, it's a great piece of research.
The mission here for our deep dive is to explore this just strange and unlikely collision of disciplines. We're going to examine how a critical roadblock in developing this futuristic climate-saving glass was actually solved by reviving an ancestral glass-making technique.
Which is wild to think about.
It is, and we'll get into how modern artificial intelligence was required to understand the atomic physics of why that ancient trick actually worked in the first place.
The contrast between the tools involved here is just striking. On one end, you have these trial and error methods developed by artisans like thousands of years ago.
Right, literal ancient history.
Yeah. And on the other end, you have the most advanced algorithmic models available to modern chemists today.
So the researchers essentially had to bridge these two eras to solve a manufacturing problem that was keeping this revolutionary material basically trapped inside the laboratory.
Exactly. They had to look backward to move forward.
Well, let's establish what that material actually is before we get to the roadblock itself. The research centers on something called MOF glasses.
Right. MOF.
Yeah. And if you picture traditional window glass at the microscopic level, it's this amorphous, chaotic jumble of silicon and oxygen. Like, it lacks a defined crystalline structure.
Right. It's very disorganized.
But MOF stands for Metal Organic Framework. And just hearing that, it implies something highly ordered and engineered.
It is. A metal organic framework is a fundamentally different architecture. I mean, it's a hybrid structure.
Okay, hybrid how?
So you start with metal atoms, or clusters of metal atoms, and these basically function as the structural nodes.
Like the joints in a scaffolding?
Exactly. Then you connect those metal nodes together using organic molecules,
Yeah.
and those act as the struts or the beams that span the space between the metals.
Okay, so if I'm visualizing this correctly, instead of a solid block of fused sand, a MOF is more like microscopic scaffolding. Or maybe like a three-dimensional molecular sponge.
The sponge analogy captures the mechanics perfectly, actually. The defining characteristic of a MOF is its porosity.
The empty space.
Yes, the empty space between those struts. Because chemists can swap out different metal nodes and different organic struts, they can engineer the exact size, shape, and even the chemical properties of those internal voids.
Meaning you can essentially design the empty space to attract and capture a very specific chemical target.
Exactly that. You can calibrate the electrostatic charge and the physical dimensions of the pores to perfectly match, say, a molecule of carbon dioxide.
Wow.
Or a molecule of hydrogen gas. So you pass a mixture of gases through this framework. The target molecules get trapped inside those tiny cages through chemical adhesion.
While the rest of the atmospheric gases just flow straight through unhindered.
Yep, they just pass right through.
I mean, that presents a massive opportunity for industrial applications. If you have this porous framework that acts as a targeted sponge for the exact gases driving climate change, the logical next step is just deploying it everywhere, right?
You would think so, yeah.
We should be lining industrial smokestacks and exhaust systems with this material, but obviously that isn't happening yet. So if we have this miracle material that can trap CO2, why aren't we building them everywhere?
Well, the barrier to real-world deployment basically comes down to how MOFs are synthesized.
Okay.
When you create a MOF in the lab, it usually precipitates out of a solvent as this very fine crystalline powder. and a powder is notoriously difficult to use in heavy industry.
Oh, I see. Because it just blows away or washes away.
Right. If you want to coat a filtration membrane or line a pipe or build a durable structural component, you really need the material to be in a glass state.
So you need to melt that powder down so it flows, shape it into whatever form you want, and then let it cool into a durable, solid barrier.
Which brings us back to the traditional rules of glass making. You have to apply heat to achieve that workable molten state.
And I'm guessing that is where the chemistry breaks down.
That is exactly where the chemistry breaks down. MOFs are incredibly sensitive to thermal stress.
Okay.
The Nature Chemistry paper focuses on a specific, highly promising MOF called ZIF62. To get ZIF62 to the point where it softens and actually begins to flow, you have to heat it to roughly 300 degrees Celsius.
I mean, from a purely thermodynamic standpoint, that doesn't sound insurmountable for industrial manufacturing. We heat things much hotter than that.
You're right, the temperature itself isn't the problem for the furnace. The problem is at a fatal threshold for the material itself.
Wait, fatal?
Yeah.
Yeah.
At 300 degrees Celsius, the thermal energy is finally high enough to soften the overall framework, which is what you want. However, that exact same amount of thermal energy is also sufficient to break the covalent bonds within the organic struts holding the framework together.
Oh, wow. So the margin of error just doesn't exist.
It doesn't.
The moment the material becomes pliable enough to actually shape it, the internal scaffolding is already beginning to disintegrate.
Exactly. The material degrades into this useless charred residue before you can form it into a functional membrane.
That is incredibly frustrating.
It really is a catch-22 for the scientists. They were trapped in this paradox. The thermal energy required to mold the glass is completely identical to the thermal energy that destroys the glass.
So to make this viable for mass production, they somehow had to force those two temperatures apart. Like, they needed the glass to soften at a much lower temperature while still maintaining the structural integrity of those organic struts.
Precisely. And according to the research, an international team, primarily involving scientists from the University of Dortmund and the University of Birmingham, they realized that historical glassmakers had faced a remarkably similar thermodynamic problem.
Right, going back to the ancient techniques.
Yes. If we look back at ancient civilizations trying to work with pure silica, they faced a massive technological hurdle. Pure sand melts at over 1,700 degrees Celsius.
Which is incredibly hot.
Very hot. And the wood-fired kilns available in antiquity simply could not reach or sustain those temperatures.
So they couldn't melt their primary raw material. How did they manipulate it then?
They introduced chemical impurities.
Oh, really?
Yeah. Ancient glassmakers discovered, likely through just extensive trial and error, that adding materials like plant ash or sodium carbonate to the sand drastically altered its behavior.
Okay.
In material science, this is known as adding a flux. And these impurities basically disrupt the rigid three-dimensional network of the silica.
Okay, so by breaking up that rigid network, the material requires less energy to soften. Like the bonds aren't holding on as tightly.
Exactly. The flux lowers the melting point of the glass significantly. It brings it well within the range of ancient furnaces, which allowed them to shape the glass without needing impossible amounts of heat.
Wow. So the Dortmund and Birmingham researchers decided to apply this exact ancestral principle to the high-tech MOF powder.
They did. They took ZIF62 and deliberately added small quantities of sodium and lithium compounds into the mixture before heating it.
Okay, I have to push back on the logic there, because adding impurities to solid window glass makes total sense. But you just described a MOF as this highly calibrated molecular sponge.
Right.
Its entire value lies in its empty voids. So if you dump sodium or lithium into a porous framework, aren't you just clogging up the very pores you need to trap the carbon dioxide?
That is a very logical concern.
It just seems like adding a flux would ruin its superpower. Does the sodium just sit in the empty gaps of our molecular sponge?
Well, that is the exact risk that makes this experiment so critical. If the sodium merely fills the void spaces, then yes, the glass becomes industrially useless for gas separation.
Right, it's just a solid brick at that point.
Exactly. So the researchers had to test if the flux would behave the same way in a metal organic structure as it does in simple silica. And when they applied the heat, the results were really definitive.
What happened?
The addition of the sodium compounds successfully lowered the softening temperature of the MOF glass by a very significant margin. But crucially, the temperature at which the organic struts degrade remained exactly the same.
Oh, wow. So they successfully wedged the temperatures apart.
They did.
They opened up what materials scientists would call the transformation window. So the material becomes soft and workable long before the heat can destroy the carbon bonds in the scaffolding.
Exactly. The manufacturing roadblock was effectively cleared. Suddenly, this fragile, stubborn powder could be melted and molded into solid glass membranes with relative ease.
That's incredible.
It is. But your pushback regarding the porosity, that is exactly where the research had to go next.
Because they still didn't know if the pores were clogged.
Right. Knowing that the ancient trick, widen the transformation window, was really only half the battle, they needed to prove why it worked at the atomic level.
Yeah.
And most importantly, they had to determine exactly where those sodium atoms were going if they weren't just passively clogging up the pores.
Which means stepping away from the macroscopic behavior of the glass, like how it melts, and looking directly at the atomic architecture.
Yes.
But how do you map the internal structure of something that complex, especially when the crucial changes only happen while the material is actively being heated to hundreds of degrees?
It's a huge challenge, but to answer that, the investigation incorporated researchers in the UK who utilized high-temperature nuclear magnetic resonance spectroscopy.
Okay, NMR. You usually hear this referred to as NMR.
Yes, NMR.
For those of us who aren't physical chemists, how should we visualize the mechanics of NMR spectroscopy? Like, what is it actually measuring?
So the foundational concept here is that atomic nuclei have a property called spin, and this makes them act like infinitesimally small magnets. Under normal conditions, these atomic magnets point in completely random directions.
Just a chaotic mess of tiny magnets?
Exactly. But when you place the sample inside an NMR machine, you subject it to a massive, superconducting magnetic field.
Oh, so that forces all those microscopic atomic magnets to align.
Yep, they all snap into a uniform direction based on the magnetic field. Then, the machine hits the sample with a pulse of radio waves.
Okay.
This pulse briefly knocks the atoms out of alignment. And as they relax and realign with the magnetic field again, they emit their own very faint radio frequencies.
Like an echo.
Sort of. They essentially sing a specific chord.
Oh, I like that.
Yeah.
And I imagine the specific frequency an atom emits depends on its environment, right? Like an atom surrounded by rigid metal nodes will sing a different note than an atom just floating freely.
That is the key right there. By recording and analyzing those incredibly subtle shifts in the resonant frequencies, scientists can map the exact chemical neighborhood of every single atom in the material. And because the researchers utilized high-temperature NMR, they were mapping these neighborhoods while the MOF glass was actively being heated toward its melting point.
Well, wait, that sounds like an absolute logistical nightmare for data analysis.
Oh, it is.
Because you have millions of atoms of carbon, nitrogen, zinc, and now the newly added sodium. And as the heat rises, all the bonds are vibrating, stretching, shifting around. The frequencies must be constantly changing.
They are. The resulting data is incredibly noisy and chaotic. Trying to manually deconvolute those overlapping frequency peaks to visualize the real-time structural changes, it's completely beyond human capability.
It's just too much data.
Way too much. And this is exactly where the integration of artificial intelligence became mandatory. The researchers basically fed this mountain of dynamic thermal NMR data into advanced AI modeling algorithms.
So what was the AI looking for? Was it trying to build a three-dimensional model from the raw frequency data?
Yes, the AI's objective was to simulate the atomic interactions and determine the exact physical location of the sodium atoms during the heating process.
Okay.
And when the AI cross-referenced the NMR data with known molecular diagrams, it revealed the mechanism. It was a massive surprise, actually.
What did it find?
The sodium was not passively sitting in the empty voids, and it was definitely not clogging the pores.
So where was it?
Instead, the sodium atoms were actively substituting themselves into the framework. They were replacing a portion of the original zinc atoms at the structural nodes.
Wait, really? The sodium literally kicks the zinc out and takes its place as the connecting joint for the organic struts.
That's exactly what happens.
But why does that specific atomic swap change the melting point of the entire material?
Because it fundamentally changes the mechanical tension of the framework.
Ah.
In the original ZIF-62 structure, the zinc atoms form very strong, highly rigid bonds with the organic struts.
Okay.
It's this stubborn architecture that refuses to yield to thermal energy until the energy gets so intense that the struts simply snap.
Like dry spaghetti breaking instead of bending.
Great analogy. Sodium, however, forms a different, slightly weaker and more forgiving chemical bond.
Oh, I see. So if we translate that atomic behavior into a physical structure that we can picture, imagine building a large brick wall.
Okay, let's build a wall.
If you use standard stiff bricks and rigid mortar representing the zinc nodes, the wall is incredibly strong,
All
right?
right.
But if geological pressure is applied, like if the ground shifts, that rigid wall cannot bend, it just shatters.
Yeah, it falls apart.
But if you take that exact same wall and swap out, I don't know, maybe 10% of those stiff bricks for slightly flexible rubbery bricks, which would be the sodium atoms, the overall strength remains. But now the wall can flex and bend under pressure without breaking apart.
That analogy perfectly illustrates the concept of network relaxation. By substituting the rigid zinc with the more flexible sodium, the entire molecular scaffolding just relaxes.
Wow.
When you apply heat to this modified MOF, the weaker sodium bonds can stretch, slide, and reorganize themselves. This atomic mobility allows the material to soften and flow like a liquid, while staying well below the temperature threshold that would incinerate the organic struts.
So it's not like packing peanuts filling an empty box. It's really about swapping out a stiff joint for a flexible one. The flexible joints absorb the thermal energy so the struts don't have to.
Exactly.
And because the sodium integrates directly into the framework rather than sitting in the empty spaces, the porosity of the material is completely preserved. The molecular sponge retains its ability to trap gases.
Yes. The AI simulation provided the definitive proof of this. It showed the researchers exactly how the ancestral flux method manipulated the atomic architecture to widen that transformation window without sacrificing the material's core utility.
That is just brilliant. So with the transformation window open and the atomic blueprint fully understood, the implications for manufacturing really do change entirely. This is no longer just theoretical chemistry restricted to a lab bench.
Not at all. We can now transition to industrial scale. Because scientists understand the exact mechanism of network relaxation, they can intentionally design custom-made MOF glasses.
Oh, so they can tweak the recipe.
Exactly. They can tailor the melting properties of various highly complex frameworks to suit specific manufacturing processes.
Well, if we bring this back to the real world, to the environment that you, the listener, are interacting with every single day, where is this technology actually going to deploy first?
The most immediate and critical sector is energy and environmental engineering, specifically gas separation.
Capturing the carbon.
Right. We return to that idea of custom MOF glass membranes lining the exhaust systems of manufacturing plants or power stations.
Okay.
These membranes would act as highly durable, highly specific filters, capturing carbon dioxide emissions right at the source before they can ever enter the broader atmosphere.
And because the glass can be molded to fit any industrial geometry, you aren't limited by the shape of the filter. You can just integrate the trapping mechanism directly into the existing infrastructure.
Exactly. You can paint it on, mold it into pipes, whatever you need. And it also revolutionizes chemical storage.
How so?
Well, the transition to clean energy relies heavily on hydrogen fuel cells. But storing volatile gases like hydrogen safely and efficiently is a huge logistical challenge.
Right, because it needs to be highly pressurized, which is dangerous.
Exactly. But a molded MOF glass can trap and store massive amounts of hydrogen within its porous structure far more safely than traditional high-pressure tanks.
That is huge for the green energy transition.
It really is. And furthermore, they are exploring these custom glasses as specialized coatings.
Like for protection.
Yeah. Imagine a microscopic layer of MOF glass protecting sensitive medical implants or advanced microelectronics. The coating would be physically robust against the elements, yet entirely breathable on a chemical level due to those engineered pores.
Essentially, by applying an ancestral principle of glassmaking, we unlocked the industrial-scale manufacturing of a material that can trap the very gases heating up our planet today. The timeline of this specific discovery is just remarkable.
It really is a full circle moment.
I mean, we started with a highly advanced, deeply frustrating material that possessed the exact properties needed to combat climate change, but was fundamentally too fragile to actually manufacture.
Right, the raw material was literally trapped by its own thermodynamics.
And to solve that, modern researchers had to look backward. They adopted a simple chemical principle from ancient artisans who were just trying to get sand to melt in rudimentary kilns. They added a sodium flux.
Just a pinch of sodium.
Yeah. But to verify that the ancient trick didn't destroy the high-tech material, they had to subject it to massive magnetic fields while heating it, generating this storm of atomic data that could only be deciphered by artificial intelligence.
And the AI revealed that elegant solution of atomic substitution, proving that the rigid structure could be relaxed without losing its gas-trapping capabilities. It is just a flawless synthesis of historical knowledge and futuristic analytical tools.
It really demonstrates that scientific progress is rarely linear. We tend to view innovation as this process of just discarding old methods to make way for the new. Yet, in this instance, a forgotten trick of antiquity provided the exact chemical key required to unlock a 21st century manufacturing bottleneck.
It really does. Which honestly leaves us with a compelling, broader question to consider.
What's that?
Well, if an ancestral method for manipulating silicate glass was the precise missing piece needed to deploy a futuristic carbon capture technology, we have to wonder what other ancient principles are currently hiding in the historical record.
Oh, wow. Yeah.
I mean, how many other forgotten techniques of metallurgy or agriculture or architecture are sitting in plain sight right now,
Yeah.
simply waiting for artificial intelligence to model their hidden atomic mechanics and trigger humanity's next major technological leap?